that IceCube is doing, and that's looking for the extreme high energy neutrinos, the highest energy neutrinos ever observed. And today I want to take the opportunity to tell you about another thing that you can do with these kind of experiments, and that is look for neutrino oscillations with IceCube, or in general any large volume neutrino telescope that can go low enough in energy so that you can start seeing these. So let me start with a little bit of theory on neutrino oscillations. Now we have a lot of talks that will cover these in more details and that have already covered this. So let me just tell you about what you should care when you do these kind of experiments. So I'm going to have only this little part of the theory. So this is a summary of what we know of the neutrino. It's probably incomplete, but it's good enough to highlight that we know right now that the neutrinos are massive, but they're not too massive. So their masses are small, and they're not that different from one another. And apart from that, the neutrinos happen to be mixed, so that only can happen if they are massive. So this is just making use of this freedom given here. And they are almost maximally mixed, unlike, for example, the quarks. Now, if we take these three characteristics and we have a thought experiment with neutrinos, then you will realize that when you produce neutrinos, you know that they are produced in flavor bases, so they will have a definite flavor, but they're going to be a superposition of mass eigenstates. Now, these mass eigenstates are small, their masses are small, and the values are very close to one another, so actually you're going to produce superposition of all of them, because pretty much any reaction will have the energy to produce all of these states. Then, as they propagate, they're going to go into mass states, they're going to acquire phase, and they're going to travel close together, they're going to maintain coherence. When you detect the neutrinos, then you have to go over a coherent sum of your mass states, and that means that you're going to have an associated lepton flavor that is connected in the interaction here, but this doesn't have to be necessarily the same one that you started with. That's pretty much everything you need to know. You produce, you propagate as mass eigenstates, then at your detection point, it doesn't have to be the same flavor that you started with, right? So we'll go quickly through the math. This is basically all you're going to need. You need to know that there's a projection between the two bases. So you know your mass eigenstates, you know your flavor eigenstates, and there's got to be a connection. And this connection we usually parameterize as a mixing matrix, where here n is the number of massive neutrinos, and so the matrix is n plus n, and then this is the number of parameters that you need to explain these bases. Then you know that you have different masses, and if you just take these two things and you calculate transition probabilities in vacuum, you end up with a formula that looks a little bit like this. Now, this kind of seems complicated, but at the end, all you have is an amplitude and a phase. And if you go to the two neutrino approximation, which holds very well for many experimental cases, it will look just like this. So if you put the constraint that in nature we have observed 3 neutrinos, then you need a 3 by 3 matrix. You only need 4 parameters. This is a way to write the matrix with 3 mixing angles and 1 complex phase. The complex phase sits in that spot just because of the parameterization. It actually doesn't matter. It has nothing to do with the theta 1,3 angle. It could sit anywhere else. It actually needs all of the angles to be non-zero to have any effect. And then you have these 2 unique mass splittings, which happen to have a hierarchy. So there's one that is considerably larger than the other. And when you take this into account, then this formula becomes a very good approximation. And this is the same as here, but in the 2 neutrino case, where you have a single effective mixing angle when you make an experiment. And then you have a phase with, again, just 1 mass splitting, which is relevant to the case that you're studying. Now, the interesting thing from the experimental point of view, if you're going to try to measure these 2 parameters, is that you have to access these 2 observables: the length that the neutrino has traveled and the energy that the neutrino has. So I'm going to come back to these 2 things again and again, because that's the only handle that we have in experiment to try to measure neutrino oscillations. We got to measure these 2 things, and then we see the rate of neutrinos that we observe. Now, that's all for matter. For vacuum. If neutrinos cross matter, then you have ordinary scattering processes. So you have charge current interaction, neutral current interactions. The neutral current interactions will happen the same for all flavors, so you can forget about them. It's just like a rotation on your whole system. It doesn't matter. But the charge current interactions will only happen for electron neutrinos with the electrons in matter. So you can add that to your calculations as an effective potential. And then if you are in a constant matter density or constant electron density, because those are the only ones that matter, then luckily you can solve this and recycle the formalism that you developed before. And the only thing that you need to change is that now you have effective parameters that you realize only when you are in this matter. And when you have this constant electron density, you have to redefine your delta m squared and your mixing angle. And interestingly enough, the fact that you redefine your mixing angle can introduce some new effects that only happen in matter. So one of them is, well, two of them are resonances. The interesting ones are resonances, which means that it doesn't matter which value you start with your mixing angle in vacuum, you can change it to pretty much anything else if you have the right combination. Your potential, if you take this formula that I just showed back here, and you take A and then you try to make A equal to just the quantity below, then this part right here is going to go to 0, so you're going to end up with a mixing angle that is going to go to pi over 4. And if you go back to your formulas, these ones right here, if you put pi over 4 here, that's going to give you the maximal transition. So it's going to give you the maximal change between flavors. If this value, AR, is now much bigger than whatever is here in the denominator, this just becomes very large, and now you go to pi over 2, and that just means that you suppress all kinds of mixing that would have been allowed otherwise. This is a local effect because it only depends on the electron density that you have. So that's in the potential A, which I forgot to highlight here. The potential A that you're including here just needs the electron density and the energy. And those are the only two things that you can play with when you go for this kind of local effect in matter. Now there's another one, slightly more complicated. It's a parametric effect. If you have a potential that is symmetric, so you have this kind of structure, for example, then you can calculate your transition probabilities, and there a dependence appears that is connected with the difference between the effective parameters in these two layers. And you can have these kind of effects only if you have matter, right? Now, there's an interesting thing that happens with these two effects that doesn't happen in vacuum. For vacuum oscillations, the delta m squared here sits inside sine squared, so it doesn't matter what the sign of that delta m squared is. You will always get the same answer. When you come to this case, in particular, actually in both of them, the sign of the delta m squared plays a role. And that comes back to the question of the hierarchy that was discussed already yesterday. Now, what about stereo neutrinos? So there's been an idea floating around for quite a while now of adding a neutrino to the system that does not couple to W or the set. So the only way that we could note the presence of this neutrino is that the new state would mix with the known flavor states. Right? So an example, the simplest one, is just add one of such neutrinos. You can add as many as you want. If you add one, then you have three new mixing angles and another complex phase, and now your mixing matrix will look something like this, where this was your original one, and then you have expanded it with new terms that are connected with this fourth neutrino flavor. And then matter effects become different, because this was the interactions that I highlighted before that you can have with the neutrinos, but now you have another state that doesn't have any of those interactions. So before I told you can forget neutral current interactions. This is not the case anymore, because this will see neutral currents, but it's not anymore a global effect for all neutrinos. These ones are just going to pass through without seeing that, but there's still change in probabilities in between. So actually, you could see the presence of such a particle by looking at the distortions that happen when you cross matter and whether or not there is such an additional distortion. So this is just a summary of what I just said. Neutral current interactions are no longer global because there's one neutrino that does not feel them. And new mixing angles can, again, undergo resonances just the same way as I told you before. So as long as the mixing angle is non-zero, then you could create a setup in which you can enhance that value. Now, what do we know about neutrinos so far. I just told you about the possibilities. This is a very short summary of what we know. We know that all three of the mixing angles are non-zero. Two of them are large. One of them is pretty small. Okay. We know that there is a hierarchy. There is one mass splitting that is considerably smaller than the other one. And we really have still no clear idea of what happens with delta Cp. We have measured the mass spectrum of the neutrino. And we know that, well, partially, and we know that they can line up either this way, where you have M1, the lightest one, then M2, slightly heavier, and then M3, significantly heavier, or the other way around, where M1 and M2 are in the same order, but M3 is significantly lighter. Now, this is just, if you want to put values here, I just say large and small. If you want to put values to the mixing matrix, this is how things look like from one of the groups that looks at fitting all the available data from neutrino experiments. Now, this is all I'm going to say about the theory and where we stand. Now let me tell you about what you can do in oscillations if you can measure atmospheric neutrinos. So yesterday I was telling you a lot about this part, right? I wanted to know what is the source of cosmic rays. For all the purposes of this talk, I don't care anymore about the source of cosmic rays. The only thing that I care about is that those things exist. And they reach the Earth, and they arrive in an isotropic way, and when they interact in the atmosphere, they're going to produce a shower of particles, and some of those particles are going to be neutrinos, particularly muon neutrinos and electron neutrinos. This is just a very simple sketch of what I was telling you about. Cosmic rays arrive, produce neutrinos together with muons. So the same background that I was telling you about yesterday is going to be relevant again. Same experiment, same source of background. Now, there are some calculations. There have been measurements of atmospheric neutrinos. This is not new. We know that they're there. There are calculations that try to explain a little bit more in detail how the flux of neutrinos look like. And this is just a compilation of 3 groups that try to make such calculations. In how the spectrum looks like, this is flux times energy cubed. So the spectrum is dropping very sharply. And I have to multiply it times energy cubed so you can see it in a reasonable figure here. You have electron neutrinos and electron antineutrinos, roughly the same quantity of each of them. And then about 2 to 3 times higher in rate, you have muon neutrinos, and you have some more neutrinos than antineutrinos in the muon channel. And you can see here from the difference in the calculations that there's some spread in the certainty with which we know these fluxes, but the overall characteristics from all the calculations hold that they roughly are flat in e to the cube, the spectrum, and then you have the electrons which have a significantly smaller rate than the muon neutrinos. Now, here I'm just showing you, let me see if I can go back. Here I'm just showing you a part of the energy spectrum because this is the most interesting part for oscillations, as you will see, but this just continues on, right? So when you look at atmospheric neutrinos, you end up having a very wide baseline because you can look from your detector all through the Earth, which means from 12,700 kilometers to a few tens of kilometers if you just look straight up from your detector, things that happen in the atmosphere here, or if you just look through the entirety of the Earth. And you have this wide energy range that you can cover. And interestingly enough, you have the possibility of crossing different electron density paths along the different directions. So that's going to become useful later on. Now, the oscillations that you can see if you look at atmospheric neutrinos with this kind of neutrino telescopes that have a threshold at a few GeV can be summarized in these survival probability plots. These are survival probabilities for atmospheric neutrinos calculated in the full 2-neutrino formalism with all matter effects and whatnot. Here I just put the formula for reference in 2-neutrino mode if you want to remember the factors that go in. This is electron neutrinos, energy, cosine of CNIT. Cosine of CNIT is connected with the path length. Cosine of CNIT of -1 means that it crossed all of the Earth. Cosine of CNIT of 0 means that it comes from the horizon, short paths. Cosine of CNIT of 1 means that it just comes from here, so very short paths. Here I just go to 0 because basically all oscillation effects disappear after that. So at the horizon, you stop seeing anything interesting when you are at these energies. For the electron neutrinos, the disappearance when you include matter effects, which I have done here, can be kind of strong at some particular energies. And then it's pretty much uninteresting everywhere else. For the muon neutrinos, you see that there are these patterns of disappearance that look like a very nice, with a very nice periodicity. And there's a very, very strong disappearance, so they go basically to zero in this region, all of these. So that's about 25 GeV when you go straight through the Earth, and then it just moves towards lower energies when you start moving to the horizon, and then there are these multiple patterns. Now the reason why this is not smooth, you can tell that this formula is not going to give you these two patterns. That's because of the matter effects. This formula gives you only this side. This is a good approximation. When you go to high enough energies, all your new transitions are suppressed. You're too high in energy. Matter effects go to that suppression regime. But on this side, you still have oscillations, and they're actually very well described by this. So if you look only at this side, that's a very nice region for measuring theta 2, 3, and there should be here delta m squared, and to look for tau neutrino appearance, because most of these events that disappear here will appear in the tau neutrino channel. And when I say most, I mean like 90-something%. So really most of them. This region here is a region of resonances. So at these energies, the electron density of the Earth plays nice with you. So if you have the right hierarchy and the right electron density, which we do apparently for this kind of neutrinos, then you can expect these new type of transitions that would be otherwise unexpected when you only look at vacuum oscillations. It is very clear in the electron neutrino channel, because otherwise these would be pretty much empty. So there's a small vacuum probability oscillations, but you wouldn't even see it in these plots. But now you can clearly see it. It goes to a very large disappearance. And on the mu neutrino channel, you always expect some modulation here, but now these jumps that appear here are just because of the matter. And here, this sharp jump here, that's where you stop seeing the core of the Earth and just go to the mantle. So this is why there's a big change, just because you have a big change in the electron density that you cross. So if you can measure these areas, if you go to these slightly lower energies, then you will see this kind of strange patterns. For neutrinos, if M3 is the heaviest state, so if the mass ordering is normal, or for anti-neutrinos, if M1 and M2 are heavier than M3, and that is the case of the inverted ordering. So you only see it in one of the two cases. So distinguishing whether you see this or not in neutrinos or anti-neutrinos, or whether you measure the absence or the presence of these additional resonances, is a great way of identifying the true mass ordering, which we still don't know. So this is just a summary of what I was saying. If you go low enough in energies, this is a vacuum regime. It doesn't matter that much. Resonances happen from 2-ish to something like 12 GeVs. It's a very interesting region. If you go higher in energies, you have the saturation regime where you can measure oscillation parameters very precisely. Now, I told you about stellar neutrinos before. So how would stellar neutrinos look like if you search for them in atmospheric neutrinos? This is an example. Now, please note here that instead of going for all directions and a very narrow energy range, here I've gone for a very large energy range. So I start at 10 GeV and I go all the way to 10 TeV. So it's a substantially different range. And here I'm just showing you for cosine theta of -1, so crossing all of the Earth before you could detect these neutrinos. Standard oscillations are in blue. So there is this very large dip that you would expect around 25 GeV, and then there's nothing. Nothing interesting happens anymore. So you don't expect from standard oscillations anything at TeV energies. And yesterday I told you about selecting a sample of through-going muons to look for the sources of neutrinos, extragalactic neutrinos. Well, you can use the same sample to look for whether you understand your atmospheric neutrino flux at these TeV energies, because stellar neutrinos would have two effects. One of them is that you could expect the same kind of resonance effect at around TeV energies. So there should be a depletion of neutrinos at a very particular energy range, and then it would be fine again, and then you would see the standard oscillations. Or, I mean, at the same time, not or, at the same time, they produce a modulation in the low energy side because of what I was telling you before, that you have this new neutrino flavor that doesn't interact with matter at all, but now neutral current interactions are now global, so the other neutrinos do feel them, and you end up with some small modulation. So you can look for stellar neutrinos at the low energies, or also at the higher energies, at TeV energies that IceCube sees. And if you look again at the formula, it's very straightforward. If you go to higher mass splitting, which is postulated for stellar neutrinos to be in the order of 1 electron volt square, then for this ratio to stay constant, you just need to go to higher energies. And that's why you move from an effect here to an effect here, straightforward. And the reason why this effect can be large, even if theta is small, is again because of matter effects. But then again, the same game comes where you need the right hierarchy with the new mass splitting, so either normal or inverted in that new M4, and that will define whether you see this in the neutrino or anti-neutrino side. So to summarize, with atmospheric neutrinos, you have 3 regions that can be accessed if you have an experiment that is big enough to cover all of them, and IceCube is such an experiment. You can go for standard oscillations if you can measure something from 7 GeV onwards. You can look for neutrino mass ordering if you can narrow down this region and look at the 6 to 12 GeVs. And you can look for stellar neutrino signals, either in the low energy side or also in the higher energy side. And you do all of this by looking at your atmospheric neutrino flux and looking for distortions with respect to the calculations or the observations at different energies. Now let me tell you about the search for these kind of effects in atmospheric neutrinos below 100 GeV in IceCube. And all of these searches go for 4 studies. Measurement of the absolute value of the mass splitting. So as you will see later, IceCube is just at the limit where it's not dense enough to see the resonances that I was talking about, but you can still measure the absolute value of delta m square. The mixing angle theta to 3, also referred to as the atmospheric mixing angle. Appearance of tau neutrinos, which we can do because we have neutrinos at energies high enough that we're above the threshold for tau production, and the search for stellar neutrinos. So I described the detector yesterday. I'm not going to go into the detail of this, but I totally missed to describe the deep core volume because it wasn't relevant for the highest energy neutrinos. For these neutrinos, it's going to be relevant because it's in deep core that you can see the lowest energies in IceCube. Now, this is a side view, top view of the IceCube detector. This is these 5,000 PMDs. In this region that I have highlighted here, you have 500 of those DOMs that are now closer together. Instead of 17 meters in the set direction, now you have them at 7 meters apart. The strings are also closer. The distance in between 2 strings is typically 125 meters. Now the distance here is going to be 40 in the closest parts and then 70 to 75 in the slightly sparser part. So when we look at what we call the deep core volume, we basically only look at this region down here because otherwise we wouldn't see the events that are the interesting ones for us. So if we only look at these events, our energy threshold goes down from 100 GeV to 10 GeV. So we sacrifice volume, but we can lower an order of magnitude our energy threshold. The problem, again, as it was for the high energy neutrinos, is that you have a lot of muons. Now, this is particularly complicated in the low energy side because, well, it's just a game of numbers. You have 10 to the 6 cosmic muons passing through your detector for every 1 neutrino interaction. So even if you have a very small probability of misreconstructing completely a cosmic ray muon and making it look like a neutrino, if you multiply that small number 10 times to the 6, it's going to be a significant number. So we have to be extra paranoid when we use the rest of our detector to veto all of these cosmic muons so that we only keep neutrinos that seem to interact inside the volume. So another thing that doesn't help is that the geometry of the detector is such that there are some particular distances where a muon can pass all the way to deep core without really passing close to an optical module. So that makes it very easy to get background leaking in from these corridors that form just because of the detector geometry. So you have these weird muons that are more likely than your regular neutrinos. You have misreconstructions. So this is the strategy. Again, instead of using a small veto like I described before, you use most of your detector as a veto. and you reject pretty much everything that seems to leave a signal out here, and you only want to keep those things that seem to start giving a signal inside this volume. So you have to select only starting events. This is an example of one of the first higher statistics studies that we did with the core of how we can reject this muon background. Now this is already outdated, but we keep on doing similar things. We just don't have updated this plot. This is for the neutrino direction. Now it's a reconstruction. This is your reconstructed direction. You have your event rate. You have your simulation from the sum of all of your neutrinos, your expected background, and this is a simulation of neutrinos plus background. And we have the data. And these three plots are the same information just after you go 3 different steps in your selection for muon rejection. The one interesting thing is that it doesn't matter where you start in your selection, you always have good agreement between the blue line, sum of all your expectations, and your data, which is black. But the interesting thing is that you can see how the red atmospheric muon contribution starts high. This is already after some selections, but there's still some muons, particularly when you reconstruct things that seem to go to the detector from above the detector. So you have this muon background, and this hump right here is just Mies reconstructions. You don't really have cosmic muons that would cross all of the Earth. It just looks like that because the pattern that they leave in the detector is sort of ambiguous. So you can have some Mies reconstructions. And then you have your neutrino simulation. If you go these extra steps in your selection, you're suppressing the red line more and more, and then you're more and more dominated only by the green contribution, which is your neutrino. So even though we have to reject most of the events that we ever detect with deep core, we're confident, because we do tests like this, that we're doing it in a consistent way in which we are not biasing our sample, but we're keeping a nice sample of neutrinos and rejecting more and more the background muons. Now, if you get rid of all your muons, which is a huge endeavor in IceCube, then you have to understand those neutrinos that interact. And for that, let me just point out the interaction types that we have. So we're going to be dealing mainly with deep inelastic scattering, even though we're partially touching the regime where other kinds of interactions can also take place. And these 2 figures right here just show you the cross-section as a function of energy times energy, cross-section over energy as a function of energy. For neutrinos, antineutrinos, in green you have deep inelastic scattering. So you see that when you go pretty much above something like 15, 20 GeVs, deep inelastic scattering is the dominant interaction. If you go a little bit below that, then resonance production, quasi-elastic scattering become important, and we want to stay away from those, at least for now, because they're not that well understood. Deep inelastic scattering is well understood, well calculated, and those are most of our events. If you just put a threshold, this is most of what we have in IceCube. So if we just assume for now that all of our events are deep inelastic scattering, let me tell you the topologies that we can see. These are the interactions that we care the most about, right? They're all deep inelastic scattering, different flavors, and then neutral current interactions, they all look the same. If you have mu charge current interaction, then you can hope for a long track. And why you hope for that is because the long track gives you the capability of having good pointing after your neutrino interaction. Neutrino comes in, it interacts with nuclei, produces hadrons. The shower brightness of those hadrons scales with energy. And then the muon that is produced has a quasi-constant light emission, Cherenkov light. So the range is actually what tells you the energy. So if you can establish the vertex point and then how long the muon traveled, you have a good estimate of the energy that went into the muon. And if you play around in your Monte Carlo, you can fit for the light emission of your hadronic shower, and you can estimate the energy of the interaction, and as well as the direction if you have a muon coming out. Now, the problem is that not all of the new mu CCDIS gives you long muons, and all of the other interactions don't give you any particle that travels long enough for you to do this. So just take as an example, tau neutrino interactions. You produce a tau. At these energies, the tau decays essentially instantly. So you produce one shower here, one shower here. You cannot tell them apart. It just looks like one blob of light in your detector. Think about this. This happens in a 3 to 5 meter scale, including all the travel path of the hadrons. and the extension of this just scales with the logarithm of the energy. So even if you go very high in energies, this doesn't really extend enough for your detector to see. So directional reconstruction is a lot more complicated than this, but the energy is still kind of okay. Neutral currents, obviously, they don't deposit all of the neutrino energy in the interaction, so that it's a little bit more complicated. Now, yesterday I showed you how events would look like in ice cube with all the photons that they emit. This is a view of a nice event in deep core. So you can see that the information available is very limited. This is the vertex. This is a 50-meter muon traveling through the detector. It looks tiny because the detector is huge, but those are 50 meters. And all of these blobs that are appearing are domes that have collected some light. So this is the kind of information that we start with when we want to reconstruct these events. Now there's a nice thing here though. This includes noise. That hit that you see at the very end, that has nothing to do with it. That was just noise, appears there. So we have very low noise levels, so at least we know that all the light that we collect comes from the interaction. It's just not that much. So we have to live with that. We have to reconstruct this. There's one thing that you might notice here though. Most of the information comes to one string, and we actually make use of that in some of our reconstructions. So the reconstruction of events, we have two main ways of doing this. One is to look for the time of arrival within one string where you mostly have all of your information for the very lowest energies. This is an example of what you would expect for time of arrival for your different DOMs. Here they are just plotted as a function of depth. And each blob that you see here is a hit. In purple, you have the hits that come without significant scattering. Then the ones that come after that in red diamonds are those that have scattered. So they just travel through the ice. They don't travel in a straight line, so they come a little bit later. And then if you project what you would expect from your muon in this space, that gives you the green line. So just by fitting the prompt light time of arrival, even within one string, you can obtain the direction of the muon only for the zenith angle, which is anyway the most important direction that we care. We don't care that much about the azimuth. And this is an example of a track fit here in these dotted lines in this Monte Carlo. And this is just an example of how things would look like if you add 25 degrees to that original track fit. So now this hyperbola that you form is a little bit different. So this is one example of how the first analyses were done, and we're still using these for cross-checks. But in the meantime, we developed something a lot fancier, which tries to explain not only the light that arrives early, but all of the light, because we know to some extent the properties of the ice. We know which kind of scattering we can expect. So we have this structure per DOM. So we just take, for example, this one. The structure of the time of arrival could look like this, and then you fit for the entire curve that tells you the time of arrival of your neutrinos, of the light that was emitted from the charged particles that come from your neutrinos, and you do that for all of the DOMs. Now when you go for this sophisticated reconstruction, you gain not only in resolutions, because it is slightly better than this one, but also this one can only reconstruct events that have a lot of early light. This one doesn't care anymore because it can deal with the late light. And this is an example of the fast and sophisticated reconstructions. This is the median zenith resolution for the lowest energies, function of neutrino energy. This is the median energy resolution, again, as a function of neutrino energy. In solid one, you see the old fast method that for direction, it looks like it works pretty okay. It has a resolution of like 10 degrees at 20 GeVs. Now, that's not fantastic if you want to look for point sources outside in the universe. But if you just want to look at atmospheric neutrinos, that's enough for doing a reasonable analysis. The sophisticated one in this case looks like it has worse resolution, but it actually reconstructs a lot more events. So if you would select the same subset, they would overlay one on top of the other. But this additional worse resolution comes from thousands and thousands more neutrinos. So it's useful information. Another thing that the fast reconstruction doesn't give you is a direction for the cascade-like events. The sophisticated one gives you some resolution in the direction of those events. So that's a huge gain in information. When it comes to the energy side, they both incorporate sort of the same techniques, so it's not such a big difference. It's mainly on the scene and angle resolution. So in the energy, we have to typically deal with like a 30%, 25% energy resolution. So my computer just crashed. Let me open this again real quick. That's nice. The next figure that I was going to show you anyway, that's on the identification of the neutrino type. So yesterday, I was telling you that when you go to very high energies, you even want to try to identify the tau neutrinos. That's not possible anymore at all in the lowest energies. But what you can hope to do is try to identify those neutrinos that have a long enough track, and those are going to be tagged as tau, as muon neutrinos. But then again, not all of them have a long track, so you have to play this game in which you try to identify only a subset of them. And we have done that, and we basically can identify correctly sort of like 60 to 70% of the muon neutrinos, and then there's a misidentification rate of like 20% for all the other particles, just because, as you saw in that event view that I showed you before, it is not very straightforward to identify these kind of events because the detector is not very dense. This is exactly what I was telling you about. Identification of particles in deep core, this is classification as tracks. It obviously improves with energy. Be careful because this is a slightly different energy range. This is the fast one, sophisticated one. When you go to high energies, this one tends to like 75, 80% good identification. This one stops at 60 because it was an old method, right? And the misidentification is always like 25 to 30% for the other particles. So by doing this, you're going to put particles basically after you see them in two buckets, the ones that look like tracks, the ones that look like anything else. So you have suppressor background. I told you about the reconstruction of direction and energy. So now we have those two things. So these are the two things that come in here. And we have some particle ID estimator, which is not great, but it's better than no separation. That can tell you something about the flavors that you're considering. So you think, fine, now you can go and do an analysis with this. Well, no, the detector is not a kind detector. So you have to take care of all the systematic uncertainties that go in. Now I'm going to highlight a couple of the ones that are usually the ones that we are concerned about the most, or that we know matter the most. One of the largest uncertainties in the high energy studies that turns out to be not that relevant for low energies is the ice. So when you look at ice cube data, you have naturally occurring glacier that is very transparent but has a structure. This is an example of that structure as a function of depth for your absorption coefficient. It's probably easier if you think about the absorption lengths, which are on this side, and this is your scattering coefficient, again, scattering lengths on this side. Now, the nice thing about deep core is that you see all of the structure, but deep core sits in the nicer region of the detector where these values are the longest. So you have absorption lengths of the order of 100 meters or more. So that's nice because anyway, your detector, the part that we care about, is not even much bigger than this. So that's nice. The scattering is a little bit more problematic because the scattering lengths are of the order of 50 meters. So we have to model that, and we have to take that into account. And luckily for us, we're still in a regime where it doesn't matter that much what are the actual properties of the ice. We have some uncertainty bands on top of these measurements, so we can produce Monte Carlo with these properties changed. And for the analysis that we have done until now, they don't matter. So that's a very nice cross-check at the moment. Now, there is this bulk ice that was just there, but then to deploy the detector, we had to melt parts of it, right? And then we dropped our sensors, and then we just waited to let the water refreeze. This is an example. That's one of the pictures of a sensor being deployed. That's on the shallow ice. That's why it looks like this, right? So you actually drill this part with a mechanical drill, but then later on, you're just pumping hot water in to make the hole to put your sensors, and then you just let the water refreeze. So we have seen with some camera images that are in some of the strings that right when you deploy, it looks like this, and there are some lasers that are pointing in for calibration purposes. But then after some time, there seems to be some sort of cloud that forms. So the idea is that there might be bubbles that are just in the water that you have been recirculating to make the hole, and then the bubbles would tend to be trapped towards the center, and the central core produces things like this. Now this is very hard to model, and we don't have at the moment a calibration source that would be particularly good at identifying this. We have at the top of each dome a lot of LEDs that can be flashed at will to see the information that other domes see. So we can see what happens at other domes when they are like 40 meters distance, and we can see what happens at the domes on top, but they are not lasers, right? Like LEDs have diffuse light, so you have to make some assumptions to what happens in between. So at the end, what we do is that from the lateral light that comes in the domes, we can constrain very well the relative angular acceptance of the optical modules. This is as a function of the angle that the light comes from, and this is the relative acceptance coming from the side would be coming from here. We can constrain this part very well, but the very forward region, when photons come from here, we cannot constrain very well. So we have to give a lot of freedom to our simulation, to our Monte Carlo, to our checks with data, and the data actually ends up fitting this curve in this region. So that will limit our ability to measure neutrinos, but it guarantees when we give this freedom that we can avoid biasing ourselves by this lack of knowledge. Then that is the angular acceptance. We also have a global efficiency, optical efficiency of these modules, and we use the same flashers to fit for this global efficiency. I mean, all of the domes were tested in the lab, but then once they are deployed, their behavior can change a little bit. So you have advanced studies that use these flashers, light that travels in the order of 40 meters, to try to establish what is the absolute dome efficiency. Then you do have a very nice natural source. If you pick minimum ionizing muons, they have a very stable light emission, so you can use these muons to understand whether you have a correct input on your dome efficiency scale. And there are some other studies that try to look for the LED light that would travel within the same dome, so it has to scatter and come back in, on their ideas on how to use the in situ camera observation. This is just an example of how the flasher data looks like when you have to travel on the order of 100 meters. This is the time from event flashed, and then in red, this is 122 meters. You have in dashed fit, and in red you have the data used for that fit. So when you go to short distances, things seem to agree fairly well. Another thing that you have to care about, which is a little bit out of our control, the two ones before are completely related to the detector. Now you have to care about the neutrino flux, which we just use. Somebody else produces for us. We don't produce our own neutrino flux in-house. And there are uncertainties in these fluxes. This is a function of energy, the uncertainty you expect from two different calculations. This is from work that was done about 10 years ago and then reproduced recently in the literature. And this is from the calculation that we actually use from Honda. So you see that there are uncertainties on the order of 10 to 15%. They are not only energy dependent, they are zenith angle dependent. I don't have the plots for that here, but you have to account for all of these. That reduces the sensitivity, your precision, but you have to account for them to avoid any bias in your detection. So how do we do the analysis of the data? This is a very rough sketch of this. We essentially produce PDFs for all the particle contributions that we expect. And then we feed the data to the sum of those PDFs with some factor in front that changes the relative contribution. But all the sources of uncertainty that I mentioned, and a lot more that are not in this list, modify the shape of these PDFs, and also oscillation parameters modify the shape of your PDFs for your electrons, your muons, your taus, your neutral currents, and then your muon background should say there. And then the sum of all of these has to agree with your data, right? And we have the data being as a function of energy and zenith angle, and we separate the data in cascade-like and track-like events, and then we have to fit for that. We can play one game before we move forward, and that is establish the relevance of the uncertainties, because I just spent like 10 minutes telling you about them. You can test what is in Monte Carlo, your expected reduction of the error that you will measure, if you would know exactly one parameter for the different parameters that you want to measure at the end, which are the mixing angle, mass splitting, and the nu tau appearance rate. And For this particular parameter, the most important ones are the ones grouped here, your detector parameters. Optical efficiency is tightly connected with the energy scale, so with your delta m squared. So you would pin that exactly, 20% better measurement guaranteed. Not saying that we're going to do that, but it's a good exercise to know how you can invest into calibrating your detector, how you can invest your time. Then there's this flux and cross-section uncertainties. Sadly, there's not a lot that IceCube itself can do about these ones. We just take them as given from other experiments that measure them. And they're not that relevant except when you look for new tau appearance, the flux and the ratio of neutrinos that come from the horizon, the neutrinos that come from below. That seems to be the most relevant part. And then there are a lot more sources of uncertainties that were tested. They don't even appear in this list because they're not relevant in comparison with the ones that are listed here. So mainly, detector and flux are the parts where one has to make improvements. Now, taking what we know so far and taking, and this is what matters the most, let me tell you about the latest results that were actually shown only earlier this year, so they're pretty new. First, I'm going to discuss standard oscillations in the core. There's a new sample that was only analyzed earlier this year that contains in 3 years 41,000 neutrino events. Now that's a huge neutrino sample. Only 5% of those are background. And we achieve a very good agreement between the data and the Monte Carlo, and this is very important for us because we don't have a direct source for calibrating our neutrino flux. We have to trust our Monte Carlo a lot, so we have to make sure that we really can trust the results that come out of it, and we do that by looking at the goodness of fit. This is the L/E plot for cascade-like and track-like events. When you do this in L/E for the parameters that we expect, you expect the disappearance to happen in this peak right here. This is the case without oscillations in dashed purple, and your observation is down below. Here you see the breakdown in the multiple flavors. Cascade-like, it contains pretty much all flavors. Track-like, dominated by tau neutrinos, which are this green mesh. This is the residual with respect to the best fit, so it all agrees pretty well with what you have measured. These are the parameters that are included together with the priors, but I just told you about that, so I'm not going to stay here. This is the latest result from IceCube on the two atmospheric oscillation parameters, sinus squared theta 2, 3, delta m squared 3, 2. This is the green line. That's 90% confidence interval. You can compare that with other experiments that were actually built to measure oscillations. Minus, which stopped taking data already. T2K, which is still producing results. Nova, which has only started producing results recently. And Super K that has been around for quite a while. So the regions pretty much overlap. Nova seems to suggest that this value is incompatible with maximal mixing, but all the others agree with maximal mixing, including now the results from IceCube. The delta m squared comes a little bit lower than everyone else, but is really all within the uncertainties. Now, if we can measure the disappearance of mu neutrinos, which gives you essentially these contours, that means that maybe we can hope to measure the appearance of tau neutrinos in our sample. Now, I told you tau neutrinos look like a blob of light, but they come in a particular energy and direction region. So you can take your tau neutrino PDF and see if you really need that tau neutrino PDF or what scale can be applied to this tau neutrino PDF in your data and do an analysis with that, because we expect roughly 2,000 tau neutrinos. And this is showing you for these 2,000 neutrinos, the signal of a square root background where you expect these neutrinos to appear as a function of reconstructed energy, and again, cosine of the CNIT. So they all appear sort of like 30 GeV, which is close to where you have the maximum disappearance of mu neutrinos, and they all appear upgoing as you would expect. Now, if you do this analysis, you can look at your data and make nice plots that show where your tau neutrinos live when you subtract the background. So this is again the same kind of information as a function of energy. They appear mostly in the cascade-like channel, as you would expect. Some of them appear here in the track-like channel because of misidentification. And here you see this nice bump of your tau neutrinos. You can do that for the direction. They mostly appear, again, cascade channel in the upgoing part. And if you fit for the normalization of that tau neutrino PDF, this is what you observe. If the standard model and oscillations all holds and there's nothing new, it should be bang on at 1 within uncertainties. So we measure a value that is slightly higher than 1, but there's not great precision in the measurement until now. So it is 1 is completely within the 1 sigma uncertainty. You can compare that with a very similar measurement that Super K has done in the past, and they measure a much larger value, and they are actually away from the 1 normalization. So the measurement of ice cube so far seems to disagree, although still within uncertainties with the one from Super K. And OPRA, that has measured only on the order of 5 or 6 neutrinos, has this much wider band. Now, I was telling you about stellar neutrino searches. So we can do the same search in the low energy sample to look for this modulation. This has not been updated to that new sample with very high statistics. This is done on an earlier sample that was published in 2015. And you look for essentially effects that happen here where your disappearance is not as strong. And this is an example, again, of what you would expect to see if stellar neutrinos would be in your sample. You suddenly see more events in a particular region. This axis is flipped. This is the energy. This is the CNIT. We haven't seen anything like that, so we can exclude all of these regions when we look at the parameters U mu 4, which is this element of the mixing matrix, and U tau 4, which is this element of the mixing matrix. So all of these regions seems to be excluded. Only very small parameters are still allowed. You can compare that with the results for Super K. Now, Super K is also an unfair neutrino experiment, so many of these analyses can be done by both. And you can see that we're very much compatible in some regions, although there are better limits placed in particular parts of the parameter space. Now, I'm going to go briefly to the high energy side for stellar neutrinos. I told you about this sample yesterday. It's the same sample that we used to look for the high energy astrophysical flux. If you just go slightly lower in energies, you can look for distortions in the atmospheric flux and look for neutrinos. It has a very nice high purity. It has a horrible energy resolution because you only see part of the neutrino, of the muon that comes out of the neutrino, but you have very good pointing resolution. So that's the nice part. The effect that you would see if stellar neutrinos exist at high energies would be some sudden disappearance in the TeV regime. This is how it would look in your detector, now in reconstructed values. So the energy is totally smeared, well, significantly smeared, and the pointing is still pretty good. This is a result that was shown, I believe, already a couple of years ago. So what we exclude with the ice cube data is everything that is right of this red line, which is coincidentally the regions that are preferred by some of the anomalies that have been observed in the past, although the anomalies have usually been observed with electron neutrinos, and this is all with muon neutrinos. But if you think that it's all explained by one additional stellar neutrino, then the effects would have to appear in all the flavors. So far, it looks pretty much disfavored. Now, let me spend a couple of minutes just talking about what happens towards the future. These kind of experiments, they can measure oscillations. So you can think that if you would put just a few more sensors in there, you can lower the energy threshold enough so that you can, to start with, measure oscillations better. So these are projections of what you could do if you put 7 more strings. They're located in this part just because of, not to make them so special. You could put them all across, it doesn't matter. You would expect to have sensitivity that is much better to oscillation parameters. So if nova is right, you could measure something with that precision. If T2K is right, you would also improve, but not as much in the mixing angle, because that's a game of statistics. But you could make a much better measurement of your new tau appearance if you would have such a detector. Even in a couple of years, much better than IceCube can hope to do in something of the order of 10 years or more. Now, if you continue instrumenting your detector region, now with instead of 7, you go from 192, so that's a big jump. Then you can lower the threshold enough so you can look for the neutrino mass ordering that I was telling you about that starts around 6 GeV. So that's sort of your threshold. This is the sensitivity that you have to measuring the mass ordering as a function of sine square of theta to 3. We still don't know this parameter that well, and it matters a lot when you're trying to do these kind of studies. If you're here, depending on the ordering, you can have very nice or barely 3 sigma sensitivity, and on this side is essentially 3 sigma after 4 years of operating a detector that looks like this. So let me go back quickly to the present. I started with this telling you about what we know about the neutrino. Now I'm listing around it the experiments that give you the information about this. In the last few years, neutrino telescopes, very large neutrino telescopes, have started contributing in some of these fields, and there are some ideas that could continue to contribute in here. And the reason why these experiments can do this is because you have, when you look at atmospheric neutrinos, this very wide energy range and these very different baselines that if you look at them in these plots, when you look for standard oscillations, the delta m squared is what defines these lines. That is where you would see effects. So you have all of this crossover between these kind of experiments that are here in blue and all of this line that shows you where the effect is. So you have all of this on-off source region, and you have this very large effect that appears in a lot of your data. Compare that with experiments that are tuned to measure these, but they have a single baseline. They can only probe one slice in this direction. They have some energy spread in their beam, but they can only probe one slice. So it's a slightly different game when you can access this very L over E region of your parameter space, and you have multiple neutrinos. If you can separate them a little bit, that gives you a lot of information that reactor and accelerator experiments can't give you. And you can do these tau neutrino studies just because you can look at neutrinos that are high enough energy that you're above the tau production threshold. So I think really the summary from my side on this kind of studies is that more is yet to come. Thank you.
Okay, we open the session for questions.
You say you only take the flux, but you don't calculate it yourselves. Do you know what are the assumptions for calculating the flux?
So flux calculations are pretty straightforward because it's really just particle physics. There's nothing fancy about it. The problem comes from the input required for these calculations. And one of them is that you need a cosmic ray spectrum for each of the particles that matter. Now for these energies, it's mainly proton and helium, so we're fine with that. We have direct measurements even from satellites, so AMS-2 has these very nice measurements, so they have very tiny error bars. So that's one part. You need atmospheric conditions, which are monitored with satellites, so you can model that better and better every time. The problem always boils down to hadronic interaction models, because experiments, when you look at these neutrinos, you have the interaction, the neutrino comes very boosted in the forward direction, and we don't really have that many experiments that can cover any of that region. So you have experiments where your particle emission comes at a different angles, and then you extrapolate to what happens in this regime. So the improvement can come mainly if you have a better understanding of what happens in there. And the sad part is that the theory is not that great, and the experiments are not that great. But we have more data than the authors have incorporated at the moment, so there can be some improvement in the next couple of years on this. But the calculations themselves are easy, relatively easy. It is the inputs that matter the most.
Question about your reconstruction.
Mm-hmm.
Don't you, in the end, or at the very most basic level, do you do some sort of time and charge likelihood fit to determine the?
Yeah, so I didn't.
Doesn't what you mentioned just was the information about the timing?
Yeah.
But didn't quite mention things about the charge. And when that charge prediction comes into play, you then need
Yeah.
to know very precisely the optical properties. So to what level is that smooshed out? Or
Mm-hmm.
how precisely do you need to know the
So
for this to work?
I didn't go into the detail of that, but the sophisticated reconstruction is a full likelihood that includes time and charge. So what I showed was just the charge being in time. So that was a simple example of that. In the meantime, we are going through a recalibration campaign of all of the detector. And we noted that there were some assumptions that were wrong on the behavior of the PMTs. So we had SP template that would apply to all of them, and the variations are big enough that that doesn't hold. So we have to measure each one of them individually, which we can do in situ. And because of that, we have, until now, used reconstructions that work with a charge or no charge probability. So we have the option of going to the full scaling of the charge, but at the moment we removed that information because we saw that there was some discrepancy in our modeling on the Monte Carlo. So while the likelihood is there and we could use all of the information, at the moment we decided to throw away the absolute charge collected in each tom. And we still take the time profile of when they see charge, but it doesn't matter how many photons they think they have observed. That information, putting it in, makes a small difference, but it does help in the reconstruction of the events. So eventually we hope to put that in once we finish this recalibration campaign, but at the moment we just had to get rid of it.
Thanks.
So you mentioned several times that Newton interactions produce showers, and that most of the tracks that you see are because of mist reconstruction. But there is a significant fraction of Newton interactions that produce tracks. So I expect that actually most of the tracks seen from new taus are not mist reconstruction, but are actually tau decay into muons.
So that's right. 17% of the decay goes produces a muon, but if you just follow the energy, the muon that is produced is very rarely high enough in energy so that it passes this threshold of like 20 meters where we can still see the muon. So most of the taus are like 25 GeVs. Then you have the first, most of the tau neutrinos, right? Then you have the first interaction where you produce a hadronic shower and the tau. So the tau lepton, let's say, takes half of that energy, that goes to 12 GeVs. Then the tau will decay, and then only in some of those decays you will take 5 GeVs that you need into the muon that goes out. So we started thinking that, and we looked overall Monte Carlo many times, and it was really hard to find. We found those events, but it was really hard. So it looks more and more like it's mainly mist reconstruction, then there's a small fraction that actually produces long tracks. But in principle, you're absolutely right. There are muons that come out of there.
And I have another question. I haven't seen any of those this analysis. When you go to very like bingo-like detector, have you tried to see if you could say anything about theta 1,3?
So
because usually you just input the value, but have you
we
tried
use
to-
it as a systematic uncertainty.
Yeah.
We wouldn't be able to measure it.
But you should be able to get a handle on it, because you need it to be different from zero.
Yeah, you need it to be different from zero, but if once it is different from zero, because you have this wide energy range and you have this varying electron density, you essentially theta 1,3 just changes. Let me go back real quick. It's gonna take a second. It's almost at the beginning. So here, essentially theta 1,3, what's gonna do is that it's gonna move this a little bit this way or a little bit that way. And our energy resolution is not enough to see that. So we do need the parameter to be non-zero for that blob to exist to begin with, right? But the actual position is not gonna be defined well enough after you apply reconstructions. If you would have a very good reconstruction, then you can do that. Then you can measure theta 1,3 at the same time.
More questions? I have one that I was just trying to estimate, compare the comparison with Super K, that you basically can get a better uncertainty, right? You only use the deep core, and that the detector is larger than Super K, but then you go to GeV energies, so you lose like 1 or 2 orders of magnitude on the flux. So the number is smaller because of this uncertainty in the neutrino flux estimate that you show that basically goes up at lower energies. Or how does that compare? I guess I couldn't.
So, to give you the best answer, I would have to redo the Super K analysis to figure out what matters, but I can tell you roughly what I think is happening. First of all, we collect way more events than the rate of data collection is faster than Super K. So if you look at their final analysis after 20 years of running, they have more or less the same number of events that we have. their energies are lower because of the detector size, and they are in a regime where most of their stuff is not deep inelastic scattering, so they have big uncertainties on the cross-section. And we have played with all of these, and in our case, it matters very little. We have played with all the uncertainties that we could find on deep inelastic scattering calculations. It plays a very small role just because what we think we know about the cross-section is much better. And another thing is that the energy estimation in super K, again, because of the detector size and the cross-section and the kind of interaction that you have, is not the best. And we seem to be doing better in that regard. So we're doing a little bit better in the measurement. It's not so much better that you would, totally disregard super K, but it comes with the cross sections and the fact that the statistics are pretty similar by now, and the energy estimation. That's a pretty big differences.
And the other one is more like a comment than a question. So just adding these 7 strings to deep core, that will give you this 3 sigma or more than 3 sigma in the lower
the 7 strings do not help when it comes to the hierarchy, because that is a very complicated question. They help only for your measurement of tau neutrinos, and they help as a proof of principle that you can lower a little bit your energy threshold.
Okay.
So you need to do the full scale 126 strings.
126.
Yes. It's a big difference.
How expensive is that, I guess my question goes. Well, my question goes that you have a detector, and I see that it might be cheaper to do an upgrade with those if you have already done it than building a new detector, right? I mean, I'm trying just to compare with Hyper-K and.
It's so the ballpark number that people mention is on the order of like 40 to 50 million. It depends very much on how you do the accounting, whether you take into account only the hardware and or the time that it will take to deploy, or the people that are involved in all of these things. But it's in the order of, let's say, 50. Keep it like plus minus 50%. That should be reasonable.
Still cheaper, right?
It is substantial. So that was one of the main selling points at the beginning, that it would be substantially cheaper than going for these Hyper-K type experiments.
Yeah, that's right.
But the physics case is also more limited, because doing delta CP with this kind of experiments would be extremely challenging. So nobody thinks that you can do this until now, unless you would go for an extra layer of strings on top, and that some theoreticians have proposed that, and they call it super Pingu. There's a paper around. You can look it up if you want, but that's it's kind of far-fetched.
Okay. Oh, okay. Yeah. Are there any other questions? If not, let's thank our speaker again.
Thank you.
So there is a coffee break. We will come back in 20 minutes for the next for the second part of the morning session.